Awesome. Good morning and welcome if you're joining us on the YouTube video, which, by the way, all the YouTube videos are uploaded, including the practice problem or the problem that I said I would go over from your homework yesterday, right? That was dealing with the e to the negative exponents and solving that out. It's only 10 minutes long, so if you want a really good, detailed explanation, go ahead and check out the YouTube video for that. Everything else should be posted. I haven't posted your homework assignment submission file yet. I'll go ahead and do that today. Other than that, yesterday we just went over some review. We also went over some more in-depth problems using not the squeeze theorem, the intermediate value theorem. Okay, so we were able to use the intermediate value theorem to basically prove that there was a root in the equation, right? In other words, the graph crossed the x-axis at 0, right? X equals 0 at some point between two values using the intermediate value theorem. That's a really good tool to have going forward into Calc 1A, and it'll show up consistently throughout the rest of your calculus courses. So go ahead and review that if you need to. Otherwise, today we are going to, I believe we left off on 2.5. So today we are going to jump into 2.6, limits at infinity and horizontal asymptotes. This is actually what we were just talking about on that website, which I shall not name on the recording. But if you're here, yeah, you have that link now, so that's perfect. I'm going to go ahead and just kind of talk about some things briefly here. Let me share my screen. As I'm getting that shared, ooh, is there comments? No, there's not. Oh, wonderful. Yeah, let me share my screen here. I have sad news. My coffee maker died this morning, so I was not able to drink my coffee. And I don't think I'm going to be able to drink coffee, so I am extra tired today. I don't know if you can tell. You're like, wow, he's not talking as fast. Yeah, rip coffee. Not even me, just the coffee maker. I see how it is. Fine, whatever. I'm kidding. Yeah, the coffee maker. Poor coffee maker. Yeah, it's probably because, like I said, the last time I had a cup of coffee was like 2 years ago. Okay, and I've had like 3 cups every day. So the coffee maker is just like, how could you do this to me? And it just died. And I'm like, fair enough. I can't expect it to do too much. It was. Yeah, I was using my coffee maker. It was tired of being used. You're right. That's just so sad. That's so unfortunate. Okay. Let's talk about some limits. We've been going over limits for the past few days. Hopefully by now you've recognized that the limit as x approaches infinity, right, of 1 over x, that is simply just 0, right? Hopefully by now everyone is on the same page with that. That's really good. In terms of what we're going to learn today, we're going to start applying limits to bigger, more complex, like fractions, figuring out what that limit goes to, right? All of this fun stuff. And we're going to use some of our skills that we learned using the factoring method, the factoring method from the factoring sheet. Yes, that's right. I gave you that evil factoring sheet, but it's going to pay off now, hopefully, if you did it. 20 of you didn't. I'm kidding. Not really. All right. I don't care. Let's take the limit as x approaches infinity. The limit as x approaches infinity of 3x squared minus x minus 2, all divided by 5x squared plus 4x plus 1. Okay, for those of you that have seen limits before, you already know, you know what the answer is. What is the limit as we take this? Go ahead and type it in the chat, just so we're all on the same page, right? The limit as x approaches infinity of this, for those of you that have seen calculus before. Do we not know? Or are we just not responsive? That's okay too. There you go. Nice. All right, Allison. Yeah, 3/5. Okay. You'll see how I got there in just a second, right? Obviously, you're just looking at the coefficients in the front and you're going, oh, that's 3/5, right? Yeah, spoiler alert, the answer is 3/5. Okay, this is, I'll explain this now. A little quick rule. I'm going to talk about it first, then I'll go ahead and prove it, right? If we have, oh no, now we have nothing. Go back. There we go. If we have the same power on the top and bottom, in other words, the highest power is x squared over, the highest power is x squared. If we have an x squared on the top and the bottom, and those are both the highest powers in their respective fields, then we can go ahead and we can just take the coefficients in front of them, right? And that becomes our limit. In other words, that becomes the 3/5 is the limit as x approaches infinity, right? And I know you're probably thinking, well, wait a minute, what about the 4x plus 1 and the minus x minus 2, right? That's a valid question, right? What happens to those terms? Because obviously we're plugging in infinity to x and infinity into the 4x at the bottom, right? Well, this is kind of a not so good explanation. I'll go ahead and prove it after this, right? Think of it this way. Say we have an x squared, right? We plug in infinity, right? Infinity squared, that's well, think of it this way. Infinity squared, that's an incredibly large number, right? That is much larger than just minus infinity. Well, it is larger than minus infinity for the first part, right? But that is just great. That is much greater than just regular infinity, right? Infinity squared is infinity, right? But it is greater than infinity. Think of it in loose terms, right? We're just talking loosely, okay? Now, what if we have 4 times infinity, right? Well, 4 times infinity, infinity squared is still much greater than that, right? And we can still kind of look at 4 times infinity as just infinity, right? So again, it's not a great explanation, but in loose terms, right, infinity squared is much greater than whatever those other terms are that are much smaller than it. So we just pretend, well, we don't pretend, I'll prove it to you in just a second, right? But in terms of what I just explained to you, right, we just pretend that the smaller terms, right, those just, we don't even deal with them, right? We just pretend they don't exist. And we're only concerned with the 3/5 x squared divided by the x squared. Now, right, these x squareds cancel out. X squared divided by x squared is 1. We're left with 3/5, right? So that's the first example I want to give you. In case that it's still not solidified, let's say we have 4x plus 3, okay, divided by 2x minus 1, okay? In this case, we take the limit as x approaches infinity of this one down here in the yellow, right? These go away. Now we're left with 4 over 2, x and x. Both x's are raised to a power of 1. Therefore, we can take this as the limit as x approaches infinity is just 4 over 2, which is equal to 2. Hopefully now you can see the pattern, right? That's how you solve these types of problems when they are both the same exponent in the numerator and the denominator. Now let's go ahead and prove it. Why? Because if I don't, then you're going to hate me because you're going to have to prove it on your Math 1A midterm, not the one I'm going to give you, the one that you're going to have in September or October, more like October. Okay, so you still have a little bit of time, which is really great, by the way. So think of it this way: we're just about covered all the material up until your first midterm. Yes, it's going to be in a lot more detail, right? Yeah, I see Kamani's like, yeah, all right, it's good. It's really good. So even if you're struggling or you're, everything isn't making sense, at least you're seeing this material before your midterm on October, right? So you're 3 weeks ahead of everyone else. Perfect. Let's go ahead and prove this now, okay? You are all going to hate me. We can factor out an x squared from the top and the bottom, right? It's a nice refresher. Yes, it is. We can factor out an x squared from the top and bottom. Does anyone agree or disagree with me? Can I pull out an x squared from the top and the bottom? Yes or no? Someone tell me in the chat, please. Is everyone asleep on the other side? I can't tell.
Yes.
There we go. Thank you. Perfect. All right. I see everyone's answers coming in. We can. Yes, we can, right? Remember, 2 days ago, you told me we couldn't. I told you we can. This is where it counts. Okay, let's focus on the numerator on the top. Let's pull out an x squared from everything. Okay, x squared times. We are left with 3 on the inside. Okay, we are left with 1 minus 1 over x on the inside, right? Because if we multiply that x squared back in, x squared divided by x, that just gives us x on the top minus x. Cool. Everything checks out. Minus 2 divided by x squared. Same kind of thought process, right? Multiply that x squared back in. X squared times 2 divided by x squared. That just gives us minus 2. Cool. We didn't change the equation at all whatsoever. Let's do the same thing with the bottom, the denominator. Okay, let's pull out an x squared. This now becomes x squared, okay, times 5. Yes, that is a parentheses, not a weird looking bar or L. There we go. 5. Leave the x squared out. Okay, so now there's a 5 plus 4 over x. Okay, hopefully everyone sees how I got this. Plus 1 over x squared. Any questions how I got to this step? Now you can see where it counts, right? So again, I'm sorry for giving you that very awful factoring worksheet at the very first day. it's tricky. It's really tricky, right? But it's going to help us in this problem, and it's going to help us for the rest of calculus, right? This is where it counts. If we were to plug in infinity, right, the limit as x approaches infinity, right? If I didn't tell you that rule, okay, you probably would have been a little stuck if you've never seen this before. You would have been like infinity squared times 3 minus infinity. What? How do I cancel this out? I'm so confused. This makes no sense, right? Intuition might have told you, okay, maybe I can do something canceling stuff out. It's still not making sense, right? But now we went ahead and we factored out an x squared from the top and the bottom. We said that we're totally okay to do that. It didn't change the equation whatsoever because we know that as long as we are dividing by whatever we pull out, right, that's technically just 1. Cool. Now we can see right away, we have an x squared over x squared. What happens to those? Those cancel. Boom. I'm going to get rid of those, right? X squared divided by x squared, that cancels. I'm going to go ahead and rewrite this down here. We now have 3 minus 1 over x minus 2 over x squared divided by 5 plus 4 over x plus 1 over x squared. Boom. Just like that. All right. Now we're in a much, much better spot. We take the limit as x approaches infinity. All right. Let's go term by term here. Okay. We plug in infinity everywhere that there's an x. Okay. Let's focus on this right here. Okay. 1 over infinity. What is it? 0. I'm getting 0. Do people agree in the chat? Everyone see how I got there? 0. Nice. Jonna, I see you. 0, right? Boom. That goes to 0. Remember that notation? Draw a line through it, put a 0. I'm just saying that term goes to 0. Okay. 2 divided by x squared. Plug in infinity for x. What is anything divided by infinity, let alone infinity squared? It's still 0, right? There it is. Yes. Thank you, Jonna. Boom. 0. Okay. Are we done with the top? Yes. Let's plug in x's at the bottom. Okay. What is 4 divided by x when x approaches infinity? 0, right? The same thing. All right, you can see where I'm going with this. This term goes to 0. This term goes to 0. Okay, so we are left with 3 minus 0 on the top. Yes, I understand that that's redundant. Okay, we don't have to add those zeros in. I'm just writing it out in case you're a little bit confused. Okay, so you can see that the zeros represent those terms that we just canceled out, right? This is just 3 divided by 5. Other words, 3/5. That is our final answer. And that is how you can algebraically prove, right? See how we just proved that the limit as x approaches this scary looking thing is simply 3/5, right? Now, for those of you that have taken calculus before, obviously you just said, oh, we have x squared, we have x squared. Those are the two highest powers in each. Boom, 3/5, we're done. The reason why we can do that is because of this proof. Now, when you get to Math 1A, right? I saw it on when we were talking about that one website that shall not be named, right? We saw one of your test questions from one of the professors was this, but they wanted you to prove it. That's how you prove it. You never learned this proof. You just knew that it was 3/5. Yeah, see, and that is where the teachers, right? Some teachers like to teach you what you need to know. Other teachers like to teach you why you need to know what you know. In other words, some like to just teach to the what, others like to teach the why, right? So that is the why explanation now, right? We were able to cancel terms out. We didn't change the expression whatsoever. Why? Because we just simply said, oh, we have a, what was it, a -2 on the top or something, right? And then we said, can we factor out an x squared, right? A week ago, you would have been like, no, you're crazy. Now you're just like, yeah, that makes sense, right? X squared times -2 over x squared, right? What happens, okay, well, these x squareds on the top and bottom cancel out. We take the limit as x approaches infinity. Now we can see this whole term goes to 0. I mean, it's awesome, right? So that is how you can, and if you need to go back and rewatch that, go ahead and YouTube video, slow it down a little bit. Hopefully it'll make a little bit more sense. But yeah, that's it. That's why we know we can take that 3/5 and just call it done, right? So does that extra proof take an extra minute? Yes. Is it worth it? I think so. I think it's really cool to do it that way. Plus, you probably won't have an option on your midterm in October. So, just get used to that kind of thought process and thinking, right? Good. That's the one clear-cut example that I wanted to talk about. I see stuff in the chat. Okay, no, we're good. Any questions there before I move on?
Can you explain how you got, like if you go back, can you explain how you got the x and the x squared? Like the 1 over x and then the minus 2 over x squared, and the same with the 4 plus 1?
Yeah, okay. So I'm gonna delete this really quick. Okay, so this is our original equation that we started with, right? Right. So I was like, right? I'm not hearing a response. Sorry, totally forgot. It's Zoom. Yes. Okay, I know you're listening. This is our equation that we started with. Are you okay if I just take this top term, right? And I can show you how we got the 1 over x and the 2 over x squared. Are you okay if I just focus on that top part right now on a separate page?
Yeah.
Okay.
Yeah.
So I'll go ahead and do that really quick. So we have 3x squared minus x minus 2. Boom. 3x squared minus, oh my gosh, I forgot it already. I'm not kidding. 3x squared minus, what was it? Someone, 3x squared minus x. Okay, sorry, minus x. Excuse me. It's because my coffee died and I didn't have my coffee this morning. Okay, don't blame me, blame my coffee maker. Minus 2. There we go. You know what? That's not even a 2. This is a 2. Boom. All right. Now we're here. How on earth did we get x over or 1 over x, 2 over x squared? Okay. Again, remember what we've been talking about the past few days and the factoring worksheet. Are we able to pull out an x squared from every single term here? In other words, right, if this was x squared plus x, right, we could factor out an x. This would just be x times x plus 1, right? This is a hypothetical situation. You can see how we pull out an x because there's an x in each term. Is there an x squared in each term here? Intuition would tell us no, okay? Because we've been dealing with calculus for the past 7 days, our actual intuition would tell us, yes, we can, right? If we pull out an x squared, right, what are we left with on the inside? Well, if we pulled out an x squared from the 3, we're just left with 3, right? If we pull out an x squared from an x, well, you can only pull out one x. And if we're going to pull out one more, right? So we just write the minus sign. That's where the minus sign comes from. Okay. So we pulled out an x, but where did the other x come from, right? Well, if we write an x down here in the denominator, do you see how if we multiply this x squared back into this term, x squared divided by x is simply just x, and it gives us this original x. It gives us our original equation back, right? That's all I
Yeah.
did. So I pulled out an x squared, right? I rewrote it in such a way. I think I talked about it in lectures 2, or maybe the first day. Okay. I think I showed you all how to like tackle these problems, right? But that's the kind of thought process here is I can rewrite whatever. If I pull out something on the inside, I can rewrite the inside so that when I multiply it back in, it gives me the original equation. Okay. Same thing with the minus 2 here, right? Do I have an x squared from this? Of course I don't. Do I have it in the denominator? Oh, I see it now, right? We're not pulling an x squared from the denominator. We're pulling an x squared from the top. And in order to pull an x squared from the top, if it doesn't exist, okay, we have to now add it back into the bottom, right? That is how I got the x squared times 3 minus 1 over x minus 2 over x squared. Okay, it's the same exact process for the denominator, right? So now you can see, right, if we pull down an x squared from the top and bottom, okay, these x squareds cancel out, boom. Now we take the limit as x approaches infinity, right? This becomes 1 over infinity, which we said was 0. This becomes 2 over infinity squared, right? Infinity squared, okay, that's also 0, right? That goes to 0, that goes to 0, okay? We're left with just 3 on the top, right? Same thing with that bottom, we're left with 5, 3/5. Question, go for it.
Can you quickly explain why 1 over 0 is infinity? Just kind of refresh my mind.
Yeah, let's talk about that really fast, okay? 1 divided by 10, okay? That is 0.1. 1 divided by 1,000, okay? That is equal to 0.001. Are you with me? This makes total sense, right?
Okay, yeah, I remember. Yeah.
Okay, now you
Like
remember.
bigger
Divided
numbers.
by an infinitely large number is going to give us an infinitely small number. In other words, 0.00000. We're going like it's 0. Okay, 0.0000. That's 0, right? Same thing if the reverse. Okay, I know that we've already just really fast. 1 divided by 1/10. Okay, 1/10 is a small number. Okay, 0.1. Flip the fraction, that equals 10, right? 1 divided by 1/1,000,000. Okay, that's 1 like that's, you see where I'm going with this. 1 divided by 0, that gives us infinity. Cool. Hopefully that clears things up. Yeah, again, if you have questions, feel free to interrupt me at any time. I really want to make sure that you all get this, right? And so even those of you that, yeah, even if you want to private message me and I'll go over it, through the chat, totally cool with me too. Hopefully everyone's on the same page now. That's really good. It's 9:40. Yeah, let's just go over a few problems here. So that's all I really want you to know from this. Same thing here. There's so much that we could cover with this. The biggest thing is, okay, let's talk about this type of problem really quick. Okay, so if we have x to the fourth, 3x to the fourth over x to the cube, right? Does anyone know what this limit is? The limit as x approaches infinity. Does anyone? All right, I'm seeing 0. I'm seeing some people are saying infinity. Some people are saying 3. Anyone else? Anyone else? Anyone else? Some people are saying 3. All right, I'm seeing people are saying 3. Okay, yeah, let's talk about this. So, okay, ooh, is it 3 or infinity? That's a great question. Now you're starting to make me question myself, right? Yeah, so the one other rule, and this is on page, sorry, in your textbook, I'm trying to find it. I believe this would be page something of your textbook. First, actually, no. Before I give you this, I want to give you this problem really quick. Okay, yeah, people are saying it's infinity. Yeah, literally, just cancel out these. Yeah, that's where I was going with that. Cancel out what's x to the fourth divided by x cubed. Okay, that's 3x over 2. Okay, you can see this goes off to infinity and beyond, right? Buzz Lightyear, Toy Story, one of my favorite movies. Yeah, right. This is taken off. That's where I was going with that. The one problem I wanted to show you first before we got there was, what if we have, let's say, this equation right here, the square root of 2x squared plus 1 divided by x, okay? Does anyone know what the limit as x approaches infinity of this is? Go ahead and type in the chat. Let's see. Let's see if people can get it. I saw one person said 2. Does anyone else know what this is, or should I go ahead and explain it? All right, I will go ahead and explain it. So for this equation, right, this is basically how they break it down, okay? And this is kind of confusing. I'll try my best not to confuse you. They have it as close. You're very close. This is technically the negative square root of 2 divided by 3. You're gonna hate this, okay, but I'm gonna go over it anyways. You're gonna hate me. Yeah, this is a terrible problem. It's a really good problem. This is what you'll be expected to do in your math courses, okay? The final answer, I'll give it to you right now, is the square root of 2 over 3, okay? That is the limit as x approaches infinity, okay? That's what they have right there. Yeah, that's confusing. Let's talk about it. There's some similarities to this, but there's some key differences that we have to point out here, okay? So they rewrote it as this. This is page 131 in your textbook if you'd like to follow along, okay? We said this is the square root of 2x squared plus 1, all divided by x, right? As x approaches infinity. Now they rewrote the expression like this. They said this is equivalent to the square root of x, right? Squared divided by 2x squared plus 1. 2x squared plus 1 square rooted, okay? They rewrite that, but then there's also a negative sign out here in front. Why is that? Because they rewrote this as negative square root of x squared. They say, in computing the limit as x approaches, oh, I'm sorry, no, this is positive infinity, So forget that negative. If it was negative infinity, we'd put the negative out there. Don't worry about it right now, because this is positive infinity. Now, how can we rewrite this? We can now write this inside of our, and we can take the square root of the whole thing now. Does everyone see that? In other words, we can rewrite this as 2x squared plus 1, all divided by x squared, right? Now we take the square root of just this. Does everyone see how I got that? Hopefully, if you have a question, let me know. Otherwise, I'm going to keep going. All right, I'm keep going. 2x squared plus 1 divided by x squared. We can now split these up into two separate fractions on the inside. Okay, again, rewriting it, 2x squared divided by x squared plus 1 over x squared. Okay, these x squareds cancel out. Boom. We are now left with the square root of 2 plus 1 over x squared. Like that. Now, from here, we take the limit as x approaches infinity. Okay, as x approaches infinity of, hold on, I'm trying to see. Oh, I'm sorry, I gave you the wrong answer. Okay, this is the square root of 2. This is the square root of 2. I was looking at two separate problems. They were dealing with two separate things. Okay, yes, I apologize. Yes, you were right, Brian. It was the square root of 2. Okay, I'm so sorry for that. I was looking at two different problems at the exact same time. My bad. All right. Yes. Okay. You take the limits. Now this becomes, I know. Yeah. If at some point you're just like, Zach, where on earth is the 3 coming from? I was thinking the same thing. That's why I was panicking on the inside, but you probably couldn't tell. Maybe you did just a little bit. I was like, there's no 3 here. There's no 3 here. What is wrong? What am I doing? I was looking at the wrong problem. Okay. I was like, because the problem right underneath it, hold on. Let me finish this real quick, then I'll talk about it. Okay. Sorry, we get to here. Hopefully everyone is with me. All I did was I didn't change anything about the problem. I factored in that x, right? I said the square root of x squared is just x, right? The square root of x squared is just x. That's what we started with. I rewrote it like this. I then moved it to the inside. From there, all I did was reduce it into something that I know how to solve, right? Cancel out the x squared, split it up into two separate fractions. Now we are here, right? We take the limits as x approaches infinity. Okay, we know that 1 over infinity is just 0. This term goes to 0. We are left with the square root of 2. Shout out to Brian for getting that 100% correct. Yes. Let's talk about this. There is no 3. There is no negative sign. I'm sorry for that. What happened was on page 131 of your textbook, you have two different problems. One of them is the square root of 2x squared plus 1 over x. And the next problem is the square root of 2x squared plus 1 over 3x minus 5. That's where the 3 came from. It tripped me up a little bit because I was like glancing, looking back glance. So that's all. Yeah, the answer is square root of 2. Any questions for me? I think the hardest part, okay, is just recognizing that we can write this, the 2x squared plus 1 divided by regular x. Okay, I think the hardest part is just recognizing that we can actually factor this in, right? We can factor this x into that entire square root simply by squaring x and taking the square root of it. Now we can combine, right? This is now 2x squared plus 1 all over x squared. Sorry, let me write this all the way down here. I'm gonna have to redraw it anyways. Okay, does everyone see how I got there? Hopefully. Then, right, all I did was split this fraction up, okay? 2x squared plus 1 can be rewritten as 2x squared over x squared plus 1 over x squared, right? Because they have the same denominator. Boom, cancels out. Infinity goes to 0. Okay, cool. I just want to make sure. I know I'm, double doing everything, but sometimes the second time around makes a lot more sense. Then you don't have to go check out the YouTube videos, which kind of makes me sad because when they have like 4 views or 5 views, I'm like, oh, okay. So just go click on it if you're, I'm kidding. You don't have to. No, those are there for whoever needs them. Also, if you just want to go back and check things out too, right? Other than that, those are two really good problems that I believe will set you up very nicely for your homework assignment tonight. Do me a favor, okay? I'm going to give you something that looks like this. It's going to be like x cubed over x to the 4th, okay? It's going to be, or no, not x to the 4th, x to the 3rd, right? Plus yada, 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 yada. Okay, this is going to be like a 3. Don't write 3/4. I know you can write 3/4. Okay, I know we know it's 3/4. Okay, I want you to prove it to me. Okay, do the proof that we talked about in class. Hopefully hopefully everything makes sense, right? Factor out an x cubed, cancel them out, rewrite the insides, then go ahead and take the limit as x approaches 0. Okay, so if I see someone that's like 3/4, I'm gonna be like, yeah, like yeah, but like, can you prove it, right? So that's all good. But if you can't, no worries, come to office hours. Alex can help you out. I can help you out. tentatively, today's Thursday. We'll talk about it again on Friday. Saturday, office hours. Are people okay if I hold like a 1 hour session on Saturday? Would people go to that? I guess is my question. That way you can ask me any questions on the homework from the entire week before you submit it, before the deadline on Saturday at midnight. If people would utilize it, I'll be there. If not, I don't know where I'll be. Probably not there. Probably sleeping. It's been a long week. Okay, from section 2.6. 2.6. I see someone in the chat. Okay, perfect. 2.6. So look at this. We're already through 2.6. Hopefully everyone's with me. I know we've covered a lot of material, but this is a lot of good material, and I think everyone's starting to get the hang of it, which is really, really good. 2.6. Let's go with number. All right, I'll take it easy on you. Number 15. All right, that's an easy one. The answer is 3/2. Like I said, prove it to me. And let's also go with. No, I'm not going to give you a terrible problem. That's just mean. Let's go with. Wow, all these problems are so awful. I'm trying to find some good ones that are going to be good practice, but not awful, and they're all just awful. Let's go with. Okay. Tell you what. 24. Okay, 24 is a good one. Number 15, number 24. Number 15, you should be able to do in like a minute, if that. Number 24, that'll probably take you 5 to 10 minutes to figure out, just because it's a little bit of extra steps, but it covers the exact same process that I covered right now. Okay, there's a few things with 24, but for the most part, you should be able to get 24. So that is. Oh, side note, number 24, as x approaches positive infinity, okay? I know in the book it says negative infinity. Just evaluate it when x approaches positive infinity, because we haven't really talked about negative infinity as much. It's really no different. The difference is it changes your negative sign, right? So if your answer was the square root of 2, right? Then it would be negative square root of 2 if I took it from approaching negative infinity, okay? We'll talk about that a little bit later, but I don't want anyone to get confused. So yeah, number 24, evaluate it as x approaches positive infinity. If you forget and do negative infinity, that's fine too, okay? But yeah, just keep note of those two things. 2 problems from 2.6. Hopefully everyone is okay with that. Let's jump into 2.7, derivatives and rates of change. All right, this is what we've been building up to. I have about 20 minutes. That's good to get, I know, right? That's good to get a good start. I don't know if I'm going to assign homework problems from 2.7 today. Let's see how far we can get, okay? Derivatives and rates of change. So we've talked about tangent lines, right? How to find a tangent line to a curve, right? Tangent, like let's say we have the graph of x squared like this. Boom, graph of x squared. We said that the tangent line, okay, we said rise over run, right? 2 points, boom, that's the slope. Okay, in this case, we're trying to approximate that slope. Okay, that slope, we said, okay, it collapses down to a point, right? Hopefully everyone remembers this. It collapses to a point, and we draw a line that theoretically touches only at that point. Oh, that was so good. Oh, I think that's like the best graph I've drawn all school year. That was good. Okay, you know what? I'm proud of that. Look at that. Well, pretend the point's like right there instead. All right, now I'm happy. Whatever. I think that's good. It's a good explanation, right? Now we can see at that. Yes, thank you. That's really nice, right? Look at that. Boom, right there at that point. Okay. You can see the slope at that singular point, right? The slope is, let's call this a slope of +2. Okay. That's a slope of 2. So that would tell us that that's at the point 2, 2. If you took the derivative of the x squared graph, you know exactly how I got that slope at the point 2. If not, don't worry, we'll build up to it. Okay. And it was recorded. Yes, exactly. I can keep it forever. You know what? When my interview comes up, right? Because I'm gonna hopefully have an interview here next week for my internship. I'll be like, hold on, I have something to show you. And I'm just gonna pull out this graph, and they're gonna be like, what is this? It's like a colorful, like drawn graph. Like, what are you, 12? And I'm like, I drew a perfect tangent line, and with my bare hands, not even a pencil or anything. And they're gonna be like, wow, it's gonna nail me the job. Watch that. Okay. Anyways, right? We talked about this. It makes total sense, hopefully, to everyone, right? Likewise, if we, oh, there it goes. It's gone. Okay. Likewise, if we drew a different point on, let's say this side, okay, well, my eraser's still on. No, it's not. Cool. We have a point here. Okay, let's see if I can do it again. Probably not. Oh, I am on point today. Look at that. All right, that is awesome. Now I have two, right? You can see right here at this point, now we have a negative slope, right? Because we drew the tangent line right there. Okay, let's call that -2. Okay, that's a slope of -2, right? The line y equals negative 2x, y equals -2x. Okay, this is rates of change. Okay, in other words, the slope, right? The slope, we can think of a slope as the rate of change, right? How much are we rising over how much are we like rise over run, right? That in essence, that is the definition of the rate of change, right? Miles per hour, rise over run, right? Something divided by something, that is its rate of change with respect to it, right? So we have our rise, okay, we'll call this delta y, and we have our run. Let's call this delta x. Cool. So as long as we're all on the same page there, let's talk about how we can express this in equation form. Cool. This is some more definitions. Feel free to write this down along with me, okay? M, we said M is the slope, right? So we found the tangent line, okay? We said that tangent line is the slope, okay? So the slope, M, is equal to the limit as x approaches a. I'll write it capital A, of f of x minus f of a over, I'm sure you've seen this before, x minus a, okay? I'll draw this graphically so that way you can see exactly what I'm talking about here, okay? M is the slope. We said that's the limit as x approaches a of f of x minus f of a over x minus a. Feel free to write that down. Let me know when you're done, and then I will continue. Hey, look, okay, now that everyone's here, so tell you what, there is 50 of us. For those of you that were not here when we talked about the website that shall not be named, once I stop the recording, we can talk about it, okay? Since you're all here. So after class, make sure to stay a few extra minutes because you definitely missed out on some important stuff, but that's okay. I want to make sure that you get it right because at the end of the day, I don't care that you showed up late. I just care that you showed up and you're here. So we will go over it really quickly at the end of class. Cool. They're like, the forbidden website, what's happening? No, you're fine. It's funny. All right, does everyone have this? Sorry, I was waiting for recognition of someone to be like, yeah, keep going. Unfortunately, this is Zoom and I'm talking to myself is what it feels like. So cool, I got a thumbs up from Claudia. Awesome, I'm gonna keep going here. F of x minus f of a over x minus a, cool, remember that, let's graph it. Boom, like this. Let's use our x squared graph because we've been talking about the graph of x squared for so long, all right? Let's call this the point A, all right? We said this is x, okay? This is our x. This is the x squared, okay? This is at our point A, okay? What do we remember about that equation? So this is some y value, okay? This is y. This is y equals x squared, okay? I only drew half of the graph though. I'm only interested in half this graph right now for this explanation. We have y equals x squared like this, okay? What did we say? We said we take the limit as x approaches a of f of x minus f of a, right, over x minus a. Well, question, all right. We have y2 and y1 minus x2 minus x1. In this case, let's just say this, okay? Let's say this is a, let's say this is x here, okay? Oh, well, eraser's on, cool. Let's say this is the point x, right? X is just some arbitrary value. Let's pretend that this graph just magically comes out like this. So we zoomed in super close. All right, that helps me a little bit. So this is the graph of x squared zoomed in. So like this is the point 1, 1 all the way out here. Okay, so if it looks a little funny, that's why. Now this is the point x. This is the point A. Okay, all we're saying is this: the limit as x approaches a. Okay, so x, right? You have a on this side, you have x on this side. X is getting closer and closer to a, right? What happens with our y value, right? Does everyone see how this is delta y over delta x? Does everyone see that? Does everyone see how it's in that form? In other words, we have our y value at x, okay? That's this point right here. We have our y value at a, that's this point right here. We have our x minus a. So x2 minus x1, x2 minus x1, we have our y2 minus y1. In other words, delta y over delta x, and we said that is equal to the slope, right? We said m is equal to delta y over delta x, which is the same thing as saying rise over run, right? So you can see how this equation right here, all it's giving us is the slope, right? It's giving us the slope m as x approaches a. What does that mean? I've been saying it this whole time. It's giving us the limit as x gets closer and closer and closer. Oh, I'm deleting again. As x gets closer and closer and closer and closer to a, until what happens? Until x equals a, right? Because as x approaches a minus a is 0, right? I know that's a technicality, right? But we're just approaching a, right? That's why we take the limit. It's approaching a. Now we can see, oh, it just condenses to this single point. Cool, checks out. That's the slope at that point. Awesome. Hopefully everyone understands that explanation. Let's keep moving forward. Remember that the tangent line to the curve slope, okay? Hopefully I explained that well enough for all of you to understand. Now, okay, we can rewrite this in terms of h. So we said as x minus a goes to 0, right? So I'm just going to rewrite it in this form now, okay? M is equal to f of a plus h, f of a plus h. I'm using capital letters. In your book, this is page 142. Feel free to use lowercase a's. I just don't want you to get confused because my handwriting sucks, except for my graphing today. Over f of a divided by h. Cool. I'm just rewriting it in a form that looks similar, but it's a little bit different. Okay, the limit as h approaches 0. Does everyone see how this is the exact same form, just written in a little bit of a different way? Hopefully, I'm hoping that some people can be like, yeah, I see it, or like, no, what's happening? Yes, cool. Jana sees it. Nice. Brian sees it. All right, right. X minus a as x approaches a minus a is 0. In this case, we just replaced it with an h. We said h approaches 0. Cool, that's 0, right? We have f of a minus f of a on the top. This is essentially telling us the exact same thing. This is literally saying f of a minus f of a, right, as h approaches 0. This is f of a minus f of a all over 0 as h approaches 0. F of a minus f of a is 0. You're like, wait, that's 0 over 0. Yes. Does that make sense when we stare at it? No, well, that scares us. When we look at it graphically, it makes perfect sense. What is this telling us? This is telling us at the point h, okay, at the point h, as h approaches 0, in other words, we look at our x squared graph, okay, we have a singular point and it gives us the slope at that point. Oh, I messed up. You know what? 2 out of 3, that's 66%. That's like a C minus Berkeley standards. Fine. C's get degrees, right? We have a slope that looks like this, right? If it's a singular point, right, the change in y is 0, right? Because it's a singular point. The change in y is 0. The change in x is 0. But we can still calculate the slope at that point. That's what this equation is telling us. So we get 0 over 0. It looks a little scary, but no, we're right on track. Now, we just talked about that. Let's talk about, tell you what. So we said that's the slope. We can also say that that is the rate of change. Now let's get into the precise definition of a derivative. I have 10 minutes of your time. Hopefully you're okay if I take those 10 minutes. Tell you what, here's what we will do today. We will go over the definitions. I will give you one very quick example. I will give you one example and I'll give you something very similar to it. That'll be your homework problem. So it's not going to be from the book. It's going to be handwritten right here. I'll go ahead and take a picture in case you're not here and you don't see it. Okay. And then we will talk about 2.7 more tomorrow on Friday, and we'll see if I can. We have a little bit of wiggle room with time to move some sections around, so we're not going to fall behind by any means. So let's talk about the derivative of a function now. Okay. So this is the definition of a derivative. Okay. I'm going to write it like so. And it requires a little bit of notation understanding, okay? It's called f prime, okay? So f is our graph, right? If f of x is our function, okay? F prime of x simply means derivative, okay? That is the derivative of the function. So for those of you who've never seen derivatives before in your life, never heard that word, but you've heard it and it sounds very unfamiliar to you, just know this. F prime of x, that notation just means that is the derivative of f of x, okay? So f prime of x, derivative of f of x. Now, I'm going to, okay, I'll leave that up there. Let me write down the definition of the derivative now, okay? We have f prime of a is equal to the limit as h approaches 0, as h approaches 0 of f of a plus h f of a plus h minus f of a all over h, okay? Let me box that in so it's a little bit more clear. So the derivative of the original f of x graph is simply f of a plus h minus f of a divided by h, okay? That is how we calculate it. This should look familiar to you. Remember way back in like section 1.3 or 1.4, I gave this exact sort of thing to you and I said, plug it into the x squared graph, or I think it was the x cubed, right? We talked about x squared as the example. You can see it's the exact same notation. What does this also equal? I'm gonna put m, okay? This equals m, the slope, right? The rate of change. So the derivative, right? Think of derivatives as rate of change. M is equal to f prime of a, which is the derivative of f of x. That's just simply the limit as h approaches 0 of f of a plus h minus f of a divided by h. Okay. Does everyone have that written down? Am I okay to move on? Yes or no? Thumbs up, thumbs down. Or just say no in the chat if you need more time.
Like a quick second.
Yeah, go for it. No worries. I do see the thumbs up from Stephanie and Claudia. Cool. Hi. Yeah, hopefully this is making sense to everybody, right? If not, go back to your notes or go back to the YouTube video, look at the explanation that I gave for the graph of x squared and how we approached h, right, to a singular point and how we can draw a line. And, you know, technically that gives us the slope at that point, right? Even though it's 0 over 0. Okay, I'm going to go ahead and move on. I'm just going to rewrite it again in a different form, okay? F prime of, if you like the other notation better, okay, f prime of a, right? So instead of h, f prime of a is equal to f of x, right? Based off of our graphical drawing that I drew for you just not too long ago, over, oops, f of a. So f of x minus f of a, okay, divided by x minus a, okay? This is the limit as x approaches a. So you can see, all right, go ahead and write that down as well, right? From a graphical standpoint, boom, okay, go back, look at your notes. We said this was x, we said this point was a, okay? As x approaches a at that singular point, boom. This is the function on how we calculate the derivative at the point x equals a. Hopefully everyone's with me, all right? Go ahead and write this down really quick. It's just a different way to write it, okay? M, so the slope of the line at that point, right? The slope of the line at A is equal to this weird looking equation that we know how to plug in and solve for. Go ahead and copy this down. I will give you an extra like 30 seconds. And then I will go over one example and I will give you an example that basically mirrors it. I'm just going to have you, yeah, I'll just have you, yeah, it's all good. Hopefully I explained that in a way that makes sense to everybody. If not, show up to office hours and we can help and go through it a little bit slower pace and maybe clear up some confusions that you might have. But other than that, the derivative is just the slope of the line at a singular point that we now know how to solve by taking the limit of, right? So instead of getting 0 over 0, we now get the slope at that point, which is wonderful for us. It opens up the door to, well, just about every single engineering aspect that you will ever come across in your entire life. So this is very important and hopefully I am explaining it good. Yes, hands, go for it.
Did you say that the derivative is just the slope of the line?
So the derivative is the slope of it's the slope of the tangent line at a singular, at a point on the graph, right? So I'll explain this one more time. Okay, you have x squared right here. Boom. Okay, we can pick multiple points. All right, we can say there's a point here, there's a point here, there's a point here. Okay, if I were to draw 3 separate lines through like that only touches that singular point, right? It would look something like that. That's a terrible graph, right? That's for this point right here. Now, if I were to get that lower point down there, okay, it would look something like this. Do you see how the slope is changing at a given point, right?
Yep.
You can also think of it as the instantaneous rate of change at a certain point, right? As you're sliding down this side, right? You're at the water park, you're sliding down the side, remember, okay? How fast are you changing at like a specific second, right? You're dropping super fast right here and right here and right here. All of a sudden, you're starting to slow down a little bit more, a little bit more. Now you're flattening out, okay? Now you're gonna come to a stop, okay? Instantaneous rate of change. Yes, please remember that. Cool. I have 4 minutes to give you one example. Okay, let's see if I can do this. All right, remember that form, f of a plus h minus f of a. F of a plus h minus f of a. My neighbor is using a leaf blower outside, so if you hear that, I'm sorry. Over h, this is the limit as h approaches 0. Okay, now I want you to do this with the function. In other words, we said f prime of x is equal to that, okay? I want you to find f prime of x of x squared, okay? I'm gonna go through this. Your problem is gonna be of x cubed, okay? I'm doing x squared. So I'm gonna show you the x squared notation, right? So y equals x squared, okay? Y equals x squared, f of x, same thing, right? Plug in a plus h everywhere you see an x, cool. This is now a plus h squared, a plus h squared, okay, minus f of a, which is just minus a squared, right? Because we said y is equal to x squared up here on the top. So minus a squared, because we just plugged in a for f of x, right? All over h. Go ahead and write this out and simplify, okay? I'm gonna factor this in my head, or I'm gonna factor this out in my head really quick using the FOIL method. A plus h squared is simply a squared, oh my gosh, a squared plus 2ah plus h squared. Yes. Minus a squared, okay? All I did was the FOIL method. That's just basic factoring out. Now I got to here. Now we cancel like terms, okay? There's an a squared, cancels out, okay? What are we left with? We now have a squared minus a squared, cool, those cancel. We are now left with on the top 2ah plus h squared over h. Guess what? I'm gonna factor out an h from everything, okay? Boom, factor out an h up here, factor out an h from here, okay? So if I write the h on the outside, the inside now becomes 2a, get rid of that h, plus h. Does everyone see how I got there? Cool. Cancel out the h's, right? Just like we did with all those other problems, so we can take the limit of it, okay? We said this is the limit as h approaches 0, okay? As h approaches 0, we are left with 2a, all right? That is the derivative, f prime of x, f prime of x. Sorry, I used a's. I know in your notes I gave you x's, same thing. So my apologies. This should be x plus h, right? This should be minus f of x. Again, a's, h, or a's or x's, it doesn't matter what variable we use, right? So in this case, it would be 2x is the final answer. Okay, I see people logging off. That's good. Your problem is going to be, I want you to find f prime of x of x cubed, okay? What is this? What is f prime of x when f of x is equal to x cubed? Cool. That is your other homework problem, okay? I want you to find the derivative using this method. Yes, I know you could easily find it doing the other one, okay? F of x equals x cubed. I want you to write it out. Just show me that you know the like how to use the precise definition of a derivative, and then you don't have to worry about it ever again, okay? So f prime of x in this case is equal to 2x when f of x, okay, when our original f of x was equal to 3x squared. If you're noticing a pattern, good, we'll talk about it tomorrow, okay? So that is our answer for the notes based off of using our limit definition that you should have in your notes. Go ahead, find the derivative of f of x equals x cubed using that same exact process. I made it identical just for the most part. Cool, I see people are logging off. If you would like to stay, okay, I'll go ahead and pause the recording or stop the recording.